All right, so we're going to be going over some elastic energy, which has to do with forces first, spring forces, and then we'll talk about some energy exerted from a spring. But first, we're going to go over forces. So this spring below has a spring constant of 10 newtons per meter. Now remember, that number right there tells us the strength of the spring. If the block is pulled 0.3, so let's go. Remember, I'm still dealing with not having any of this show up on my tablet, so it's going to look kind of weird. It's pulled 0.3 meters horizontally to the right, so that's how far this thing moves. And it's held motionless. What force does the spring exert? So we're looking for the spring force. So this block right now, what we really only care about is this spring force, so we got to know it's getting pushed to the right. It originally was here or something like that, and now it's right here. Okay, and this thing is getting pushed to the right, and then this is pulling on it back to the left with some type of spring force. So spring force automatically lets me think of Hooke's law. And Hooke's law, we can just look up real quick. I want to make sure we're actually using the right, that's not what I wanted. There it is. The right equation. Hooke's law. There it is. So spring force is equal to K times the distance the thing moved. So let's put that. No, it's not having it. Okay, so it was spring force is equal to, and that was in those little symbols, K times X. And remember, all these things mean is magnitude. So the magnitude of the spring force is equal to the spring constant times the magnitude of its displacement, of where it moved to. Okay, so I know what K is. It's 10 newtons per meter. So now I can just kind of plug and chug. K is 10 newtons for every meter of movement, and it moves 0.3 meters. So if it moves 10 newtons, or if it exerts 10 newtons of force for every meter it moves, but it only moves 0.3 meters, that means our spring force is going to be equal to 3, and newtons right here would cancel, or meters, pretty sure I said meters, so that would give us 3 newtons of force. Cool. All right, let's take a look. This one is more in line with what the Khan Academy stuff will be. A spring was at its resting position where it's attached to a wall at its left side and a block at its right side, as shown below. Okay, so there's the block. It's kind of hard to see, but the spring constant is K. There we go. The block is moved leftwards and the spring's right end is displaced from 0.25 to 0.15. So what I can do with that is I can know that the displacement, remember that's final minus initial. Well, final minus initial would give me, it started at 0.25 and it went 0.15. So that would give me 0.15 meters minus the initial one of 0.25 meters. So I know the displacement is negative 0.1 meters. Okay, and I'm actually going to make this a little skinnier. So all the positions are measured from O. What is the spring force exerted on the wall or on the block? So this is another Hooke's law type question. Same equation that we talked about up above, right? Now remember, these were magnitudes. which means the direction does not matter, only the number. So if I know this, I'm going to say, all right, spring force is equal to K, which is 75 newtons per meter. And the magnitude of the amount it moved was 0.1 meters. And now when we multiply those together, we get 7.5. Meters cancel, and our answer would be in newtons. All right, getting better at this writing without looking at the tablet thing. Let's see, uno más. Actually, that was it for spring forces. Now we're going to talk about energy a little bit. So remember, elastic energy has to do more with the energy inside the spring. Remember, it is a potential energy. So let's see, a cart has 100 joules of kinetic energy. Can I change this? No. Okay, the cart then runs into a spring and comes to a full stop, putting all of its 100 joules of kinetic energy into the spring. So that means the spring now has, so U spring is equal to 100 joules. They put all of that kinetic energy, all of it into the spring energy. So we're going to call it that. Okay. Then take a look at this info and determine how far the spring compresses when the cart is stopped. So like this. Okay. So originally the spring was like all stretched out in its happy place, and then down here it got hit by the cart and it gets compressed. Okay. So we're being asked to determine how far. So that would be delta x. So we need to know what this spring energy is. So let's take a look at our equation sheet. Spring energy right there. So potential spring energy equals 1/2 the spring constant times how far it's stretched squared. Okay. So let's see if this works again. I don't know why it didn't work last time, but oh, still nothing. Must be while I'm recording. All right. So we know that equation is 1/2 K x squared. So if there's 100 joules of potential spring energy, and we know that spring energy is equal to this equation right there, we're trying to solve for how far this thing compresses. So let's go ahead and solve for this x first. So if I do that, let's see, I would have 2, so I can multiply that 2 over. So that's gone. And then I would divide by the k. So that's gone. And then I would square root both sides. Okay. And so now I know all of these values. I can just plug these things in. So that would be the square root of 2 times 100 joules of energy divided by K, which was 50 right there. So 50 Newton meters. And that would be 200 divided by 50, which is what, 4? I have no idea what the units on that would be, so let's take a look. A joule divided by a Newton over a meter. So if we just reduce this real quick, this would be a joule times a meter over a Newton. That denominator comes up there. And then I would have, let's see, a joule. Remember, a joule is a Newton meter. So that can be a Newton meter times another meter over newtons. Oh boy. Okay. Now we get some canceling. Cancel, cancel. And we're left with meters squared. That's good. So this would be 4 meters squared in there. And when I square root it, that gives me 2. And then the square root of meters squared, meters. Boom. Sweet. Let's see. This next one is more like one of the con questions. Bruce pulls a spring with a spring constant of K equals 100 newtons per meter, stretching it from its rest length. So that's its equilibrium position is when it's at 0.2 to 0.4. All right. So let's draw this real quick. So this is like, here's the wall. Here's our little thing. It was originally it's originally at 0.2 meters right here, 0.2 meters. And then later it gets stretched. Man, I can't draw on those lines right now when it's towards the bottom. All right, that's really hard. The string gets stretched out. To 0.4 meters. All right, and we want to find from when it's happy right here to when it gets stretched this extra little 0.2 meters. We want to find how much potential spring energy gets stored in that spring. So we know the equation for potential spring energy is 1/2 K x squared. And really this is just kind of plug and chug. We know K right here, right? This is the sneaky one. To go from 0.2 to 0.4, that means that X, the amount it stretches, is equal to 0.2. It's how much it stretches between those two, right? So let's plug those in. 1/2 K we said was 100 newtons per meter. X squared would give me 0.2 meters squared. And this right here, now I just need to kind of simplify it. So 100 times 1/2 is 50. So that would be 50 newtons over meters. And this would be .04? I always forget. 0.2 squared. 0.04 meters squared. Okay. So 50 times 0.04 is 2. And let's just make sure we're getting all these. A Newton over meter times meter squared. That equals, remember, one of these is going to cancel, so this meter will cancel out with one of those meters, and we would be left with Newton times a meter, or a joule, right? So that's good. So this would be 2 joules worth of energy. All right? So that is it. We had Hooke's law and elastic potential energy. So nice job. You can't see my face, but nice job, everybody.